Hi guys, welcome to my YouTube channel. Today I'm going to teach you about mechanical waves. So let's answer this problem. So let's define first the wave here. So ang pinakamataas niya or the highest thing or the height is called the amplitude. So our amplitude will become 3 meters if you read the problem. What's the amplitude, period, and frequency of the mechanical wave shown below? So this thing is basically the wavelength. So this is the length from one trot. I don't know what's that. Just here. It is the length over here. So you cannot calculate the length here. Let me just. Okay, now let's calculate the period. So what is the period? So the period here is just these things. This 10 seconds and this 20 seconds. Let's make this better. Here. So what we're going to get the answer is just the 20 seconds and not the 10 seconds. Basically, period is just the time for a cycle. So now let's calculate the frequency. The frequency is just 1 over the period. And also defined as cycle per time. So 1 over 20 is just... Let me just use our calculator. So the frequency of this mechanical wave is just 0.05 hertz. So the unit for hertz is... the unit for frequency is hertz or seconds raised to the negative power. Now let's go to the part B. So the amplitude here, we're just going to get the average of the given. So the height, not the average, but we're going to take the difference of the height and the lowest, highest and the lowest. Okay, I thought I'm just going to get the average. Okay, so 12 minus 4 is 8 and divided by 2 is 4. So it's basically 4 meters. That's the amplitude or the height of the highest. The highest point. Okay, now let's calculate the period. So the period here is just 8 seconds. As you can see there. And the frequency is just 1 over 8. Which is... what is it? It is 0.12 5 hertz. And okay, what about in strings? So in order for us to furthermore understand what is mechanical wave, let's go into strings. When we pluck the strings or we apply the tension force sa isang string, in one string, what will happen is it will produce some kind of frequency. I don't know what it is the term, but it will have nodes, antinodes, harmonics, and I'm going to have a video on when we will see that. So I'm just going to define on what is happening here. Like this string, this is not a string, this is just... yeah, let's just assume this is a string. So we're just applying some kind of force here. And what is really happening here? We will break down the physics behind this thing. And let's go. So this is the visual illustration on what did happen on that video. So this is all of them. The formulas, I did write it. So I'm just going to write them and explain this. So this is the linear density. It is basically the density of the thing that you have used. So this is M, which represents the mass. Let me just write it in a different color. Here. This is going to be our mass. On the denominator, we have the length of the string that we use. And we have this is mu on Greek alphabet, and this is our symbol for linear density. So we also have the velocity of the mechanical wave. We can have in two terms, which is this thing and this thing. So no, the main difference between this thing is just on the bottom we have the tension force that is applied divided by the linear density. While on the other hand, on the top one, this is just for a normal mechanical wave. So this is just basically wavelength times the frequency. This formula is very common. We're going to use this a lot. And on the bottom, we have here the tension force and the linear density. So let me just write this. On this thing, we also have the fundamental frequency. So the fundamental frequency is just this thing. So this is the first one. So I didn't mention the harmonics, but I'm going to discuss it later. This is all based on the harmonics. So this is the symbol for the fundamental frequency. We can also use the last formula on the bottom. So this is velocity divided by the 2 times the length. We also have the wavelength. So wavelength can be anything. So I didn't mention the n. The n is just basically the antinodes. Okay, how can I write this? This is the length and this is the nodes. So now let's move on to this. So this is the nodes that I'm talking about. There you go. This can go on into infinity on how it will end. Can go beyond f6, f sub 6. So let me just write this. This is the nodes. And the top one is the antinodes. So on the wavelength equation, the thing that we're going to really use is the antinodes, not the nodes. So I'm just going to write it later. We're going to solve some problems. So this is the antinodes on the top one. Okay, now let's talk about the harmonics. So the harmonics is just that thing that in the circle. If you cannot visualize it though. Now let's move on to harmonics. So this one is just one circle between the two nodes here and one antinodes. This is starting from the first node into the third node. And this one is just starting from the first node into the fourth node. This one is from first node to fifth node. If you're seeing it, the one in the purple is the node. And this F5, F sub 5, the fundamental frequency 5 is just from the first node into 1, 2, 3, 4, 5, 7th node. That was too far to calculate. Over here. And this can go on forever. if the string that you use have an infinite length. Now let's solve this problem. A 2-meter long string with a mass of 0.10 kilogram is placed with a 10 Newton force of 500 newtons. So part A, what is the linear density of the string? So earlier, if you take notes of the formula, we have this mu equals to m divided by L. So that is linear density is equals to 0.10 kilograms divided by 2 meters, which is the length. So the answer here is just 0.05 kilograms per meters. So this is the linear density of the string that you have used. So part B is calculate the velocity of the mechanical wave of the string. So to calculate it, we got this equation. And that's it. And the tension force now is just 500 newtons. And we also calculated the linear density, which is 0.05 kilograms per meters. So using our calculator. Why the hell my English is so bad right now? I'm like eating my words. So this is 100 meters per second. Now let's move on to part C. Determine the frequency of the wave if it has a wavelength of 0.25 meters. So we can just use this equation. Velocity is equals to frequency times the wavelength. So we all know what's the velocity is. So it's just 100 meters per second. So the wavelength that we're finding. Oh, actually the frequency we're finding is. We just miss it. So the frequency is what we're looking for. The wavelength is 0.25. Dividing both sides, we got our answer as 400 hertz. And that's basically it for this problem. Now let's move on. A standing wave is moving at 130 meters per second on a 2.5 meters long string. What is the fundamental frequency of this wave? So to calculate the fundamental frequency, we got this equation. This is actually the first fundamental frequency. We can have multiple, like f sub 3, 2, 4, like that. So we all know the velocity. We all know the length. So we just plug it in. So we got 26 hertz. And that is the fundamental frequency, also known as f sub 1. So what is the frequency of the third harmonic? So to do that, we can just use this thing. So the third harmonic is frequency is this thing. So we all know the fundamental frequency, and we can just use basic mathematics just to solve this problem. So the third harmonic frequency is 78 hertz. Now let's go to part C. How many nodes and antinodes are present in the wave of the harmonic? So the question here is just the third harmonic. I didn't put it. I was typing very fast there. So I didn't give the formula earlier. But to easily calculate it without the use of a diagram, we have an equation. So the nodes, let's call this N sub D, because they have the same So let's put N sub D, N plus 1. So we all know what is the N. This is 3. We're finding 4. So the nodes is 4. And the antinodes, in order to calculate that, let's call this N sub A. It's just basically 3. Now let's go to part D. What is the wavelength of the third overtone? So we're going to use the fourth overtone. I mean the fourth subscript, because the third overtone is also known as the frequency of the fourth harmonic, right? And this thing is just fourth. The subscript is 4. So we're going to use that. So 2 times L divided by 4. So we got 2.5 divided by 2. And we got this. 2.5 divided by 2 is 0.62.5 hertz. O 0.625. So let's recalculate that. There is just 1.25. Okay, I did miss a thing. It is meters. And that's it for this video.